Yocto Project Standardization for AI. Imagine a world where changing your silicon provider doesn't mean rewriting your entire AI deployment pipeline from scratch, but rather flipping a single switch in a configuration file. Yet the technical reality is often a minefield of conflicting dependencies and unoptimized binary blobs that can paralyze a production timeline. The Yocto project has become the industry standard for creating custom Linux distributions for embedded systems, and its role in the AI space is rapidly expanding. For a senior engineering program manager, the challenge is not just getting an AI model to run, but doing so in a repeatable, maintainable, and scalable way across different hardware platforms. This is where meta layers like MetaTegra, MetaNXP, MetaIntel, and MetaARM come into play. The technical feasibility of a vendor-agnostic AI strategy depends on how these layers provide standardized interfaces for AI runtimes like TensorFlow Lite, ONNX Runtime, and OpenVINO. Standardization within Yocto involves creating BitBake recipes that not only compile the AI frameworks but also handle the complex dependencies, such as specific versions of Python, NumPy, or specialized math libraries like OpenBLOS. From an engineering perspective, the forensic analysis of a failed build often reveals conflicts between these layers. For example, MetaTegra might require a specific version of a library that conflicts with the version required by a generic AI layer. Resolving these dependency hell scenarios is a core task for embedded Linux engineers. The goal is to reach a state where changing the target hardware from an NXP i.MX8 to an NVIDIA Orin is as simple as changing the machine variable in the Yocto configuration, while the AI application code remains largely untouched. One of the major developments in this area is the integration of model quantization and optimization tools directly into the Yocto build process. The technical feasibility of this is high, assuming the recipes are structured to trigger the conversion of a high-level model into a hardware-specific optimized format during the build itself. This ensures that the version of the model deployed in the Linux image is always in sync with the version of the runtime and the hardware drivers. This level of automation is essential for functional reliability and prevents the common error of deploying a model that is incompatible with the target device's NPU firmware. As a mentor, I would point out that the Yocto project's move towards standardization also includes the way we handle containerized AI workloads. Many modern AI-embedded Linux systems use Docker or LXC to isolate AI services. The Yocto recipes must therefore include support for container runtimes and the necessary kernel configurations, like cgroups and namespaces, to run them efficiently. While the technical feasibility of this approach is high, it adds another layer of abstraction that can impact performance. Engineers must profile the system to ensure that the containerization does not introduce unacceptable latency in the AI inference path. Lastly, we must consider the security and licensing aspects. Yocto provides tools like the license manifest to track the licenses of all components in the Linux image. In the AI world, where many libraries have complex or restrictive licenses, this is a critical functional requirement for any commercial product. Furthermore, Yocto allows for the integration of secure boot and signed image updates, which are vital for protecting the AI models in the field. The evolution of Yocto for AI is not just about making things faster, it is about providing a professional, industrial-grade framework for building reliable AI-embedded Linux systems that can be maintained over a long product lifecycle.